The branch of physics which deal with controlled flow of electron through inert gases is known as electronics. In the beginning, vacuum tubes such as diode, triode, tetrode, pentode were used. In 1930, it was first realized that some solid-state semiconductors and their junction offer possibility of controlled flow of charge carrier. Semiconductors are small in size, have long life, are shock-proof, they do not produce humming noise, they have low cost, they are effective and reliable, they require low voltage, and they do not require any heating. Semiconductors have resistivity between metal and insulate. In a single free atom, electrons have well-defined energy levels. When two similar atoms are brought near each other, then interaction between outermost electron take place and energy levels get modified in the form of bands. This modification is due to the fact that outermost electron is shared by more than one atom. In silicon crystal, at actual interatomic separation, out of 8 n levels, 4n filled energy band gets separated from 4n unfilled band by a small energy gap. The lower energy band of 4n filled valence electron is called valence band. The upper energy band of unfilled 4n level is called conduction band. The energy gap between valence band and conduction band is called forbidden energy gap. The highest energy level which an electron can occupy in the valence band at 0 Kelvin is called Fermi level. At 0 Kelvin, the Fermi level as well as all the lower energy levels are completely occupied by electron. As temperature rises, the electron absorb energy and get excited, jumps to higher energy level in the conduction band. They become more free to conduct because they are at large distance from nucleus. Energy gap between valence band and conduction band is very small in case of metal and very large in case of insulator. In case of semiconductor, it is 1.1 electron volt for silicon and 0.7 electron volt for germanium. Therefore, semiconductor behave as insulator at 0 Kelvin and conductor at room temperature. In pure silicon crystal, the atom form covalent bond by sharing its 4 electron with the 4 electron of 4 neighboring atoms. At room temperature, some electron break away from covalent bond due to thermal energy and become free, thereby creating a vacant site known as hole. These holes can be filled by some other electron from nearby covalent bond, thereby creating new holes. The direction of movement of hole is opposite to that of electron. When electron absorb energy at room temperature, it jumps to conduction band, thereby leaving hole in the valence band. Therefore, hole in the valence band and electron in the conduction band are intrinsic charge carrier. Electric current in intrinsic semiconductor is the sum of current due to electron and due to holes. Electron being lighter have more mobility as compared to hole. The process of adding impurity in the semiconductor so as to increase its conductivity is called doping. The atoms so added are called dopant. Their size should be same as that of semiconductor atoms. Concentration should not be more than 1%. When pentavalent impurity atom, that is atom having 5 valence electron, is added to an intrinsic semiconductor, it donates an extra electron to semiconductor. Therefore, this impurity is also called donor impurity and the semiconductor so obtained is called n-type semiconductor. When trivalent impurity, that is impurity atom having 3 valence electron, is added to intrinsic semiconductor, it accepts electron from the semiconductor. Therefore, this impurity is also called acceptor impurity and the intrinsic semiconductor so obtained is called p-type semiconductor. When pentavalent impurity atom is added in silicon crystal, its atom replaces the silicon atom here and there. 4 electrons are used in covalent bonding, whereas the 5th electron remain free. Number of extra free electron donated is equal to number of impurity atoms added. Therefore, new semiconductor has a large number of free electrons as majority carriers and small number of holes as minority carriers. The 5th free electrons of arsenic atom form a donor energy level just below the conduction band. The energy gap between the donor level and the conduction band is very small, so these electrons can be easily raised to conduction band at room temperature. When trivalent impurity atom is added, then its 3 valence electrons are used in covalent bonding with 3 silicon atoms. The 4th bond remains incomplete due to deficiency of 1 electron. This deficiency of electron, that is hole, attract electron from neighboring covalent bond, thereby creating new holes. Number of holes created is equal to number of impurity atoms added. Therefore, p-type semiconductor has a large number of holes, that is majority carriers, and small electrons, that is minority carriers. In energy band diagram, holes create an acceptor level just above the top of valence band. The electron from valence band can easily raise themselves to the acceptor level by absorbing small energy at room temperature, thereby creating new holes in the valence band. A single piece of semiconductor with one portion doped with pentavalent impurity and other portion doped with trivalent impurity behave as a p-n junction diode. Hole from p side start diffusing into n side and electron from n side start diffusing into p side. When an electron meet with a hole, they cancel the effect of each other. As a result, thin layer near junction become devoid of charge called depletion layer. Due to diffusion of holes and electron, the two portions of p-n junction no longer remain neutral. P side becomes slightly negative and n side becomes slightly positive. It appears as if fictitious batteries connected across the junction with negative pole connected to p side, positive pole connected to n side. This potential difference across the junction is called potential barrier or junction barrier. It opposes the further diffusion of charge carrier. Its value is 0.3 volt for germanium and 0.7 volt for silicon. When p side is connected to positive terminal of battery and n side is connected to negative terminal of external battery, then junction diode is said to be forward biased. Forward biasing also compels the charge carrier to move toward the junction. Therefore, the depletion layer becomes thin. In other words, junction diode offer low resistance during forward biasing. Current flows due to majority carrier is called forward current. When p section of junction diode is connected to negative terminal of the battery and n section is connected to positive terminal of battery, junction diode is said to be reverse biased. In reverse biasing, the majority carrier move away from the junction diode. Therefore, depletion layer become thin. In other words, resistance increases. However, if minority carriers are repelled by battery to move across the junction, therefore they constitute the current in opposite direction called reverse current. A graph showing the variation of current with voltage across the p-n junction diode during its biasing is called characteristics of p-n junction. In forward biasing, the forward current increases very slowly up to the knee voltage, then increases linearly with voltage. In reverse biasing, reverse current also increases with reverse bias voltage. At certain value of reverse bias voltage, large current is produced due to breakage of large covalent bond. This voltage is known as breakdown voltage. The ratio of DC voltage to DC current across the junction is called static resistance. The ratio of small change in voltage to small change in current in the diode is called dynamic resistance. A device which converts alternating current into direct current is called rectifier. Half-wave rectifier convert only one half of the AC into DC. It is based on the principle that junction diode conduct when forward biased and does not conduct when reverse biased. When AC is applied, it makes the diode forward biased in one half cycle and reverse biased in next half cycle. Therefore, one half cycle is rectified and other is not rectified. A device which converts both half cycles of AC into DC is called full wave rectifier. It consists of two diodes. They are connected to the secondary coil of the step-down transformer in such a way that positive half cycle make one diode conducting and other diode non-conducting. The negative half cycle make the other conducting and the first diode non-conducting. Therefore, both half cycles are rectified and the current flows in the same direction. Filter circuit is used to make the pulsating output of the rectifier smooth. C filter consists of a capacitor C shunting that is in parallel to the load resistance RL. L filter consists of an inductor L connected in series to the load resistance RL. Pi filter consists of an inductor and two capacitors connected in the shape of pi, and this combination is connected to the load resistance RL. Ripple factor is defined as the ratio of RMS value of AC component to DC component of the output voltage. Some numericals and conceptual questions. At last, thanks for watching and listening this audio.